All right, so you've got the matrix here. And it asks you first to use row reduction to evaluate the determinant, right? So when I'm asking you to use row reduction, the easiest thing is to get it in a triangular form, so you can just multiply down the diagonal. So if I want to get it in triangular form, what should I do first? So I need to make this a 0, this a squared is 0, so I can do negative a row 1, added to row 2, replace row 2. Same thing for row 3. I just need to do an a squared. What does that do to the determinant, by the way? Nothing, good. So I get 0, b minus a, c minus a, 0, b squared minus a squared, c squared minus a squared. Yeah. And then the same idea here. I don't have to make this a 1 in order to be able to put this in triangular form, right? Because we know when we have a triangular matrix, I can just multiply it out of the diagonal. That makes life a little bit simpler. In order to get this to be a 0 here, what do I need to multiply b minus a by? B plus a? Yeah. So if you do negative b plus a, row 2 plus row 3, replace row 3. Again, doesn't change the determinant at all. This becomes c squared minus a squared times a negative b plus a. I'll put the negative sign out in front. Oh, no, it doesn't. I need a plus somewhere in here. Sorry. I'll put a minus sign in between. Try that instead. How about I write the correct answer there instead of something that's incorrect? Let's try that. Oops. And then I lied. There we go. I got to do negative b plus a times c minus a, and then add it to the c squared minus a squared. Again, those three operations that we did don't change the determinant of the matrix at all. What it does is put it into a form that we can easily evaluate the determinant now. So when we take the determinant of this matrix, I just multiply down the diagonal, so I'd have b minus a times the c squared minus a squared minus b plus a times c minus a. Right? Then I can probably make this a little bit nicer, hopefully. If you multiply out what's inside there, we get b times c, be negative because there's a minus sign there. A minus b times a, but I got a minus, so that's where the plus ab comes from. A plus ac, but again, there's a minus in front, so that's why it's minus ac. And then I get plus a squared when we simplify. Right? So then your a squareds go away. In that case. Yeah. Notice that if I factor out in this first term here, I could factor out a c, and I'm left with c minus b. And if I factor out a negative a in the second pair, I'm left with a c minus b again. So then this completely factors as B minus A times C minus A times C minus B. I did factor by grouping in that last piece. Yes.
Well, will we need to simplify it all the way down, or is the...
This one, we don't have to simplify it down to get the determinant. So in this case, no. And more likely than not, I would give you something with numbers rather than letters anyway on the exam. The reason why I did it in this case was to help us answer the last part where it says find conditions that tell us when the matrix is invertible. And so this helps me. Because how do you determine if a matrix is invertible or not using the determinant? Oh, yeah, if it's 0, it's not invertible, right? How could this determinant be equal to 0? I wrote it as a product. How could the product be 0? If one of them is 0, right? When would this be 0? If A equals B, this one, A equals C, this one, B equals C, right? So if I want it to be invertible, I need to make sure that doesn't happen. So what needs to be true about A, B, and C in that case? Yeah, they can't equal each other. They better be 3 distinct numbers, right? A, B, and C better be distinct in that case. That was the reason why I factored in that case. So that helps me answer the last part. Does that make sense? This is analogous to what we did with the eigenvalue idea, right? When we're doing eigenvalues, we were looking for the value of lambda that made the matrix not invertible so that we've got non-trivial solutions for the homogeneous system. So we set the determinant equal to 0 and then figured out what the values are for lambda. So that's exactly what we're doing here, is we're setting this equal to 0 and figuring out what has to be true about the A, B, and C if it's going to be 0, and those are the cases that we don't want. So it's the same kind of idea. But again, it helps if we factor it to get to that point. Did I need to go through the adjoint, or just calculating the adjoint okay? Okay. I'll get that answer posted on there. I didn't realize it wasn't on there. I apologize. Other questions? Yeah, listen. Number 7? Sure. Okay. So they tell you that Q times Q transpose is equal to the identity matrix. That's the definition of being orthogonal. So this is what you're given. You're asked to show. So if this is true, then you want to show that the determinant of Q is either plus or minus 1. So again, this is what you're given. So we're going to start here. What do you think you should do to both sides of the equation? Take the determinant. I'm trying to prove something about the determinant. I better take the determinant somewhere, right? So if I start with this equation, and take the determinant of both sides, I get determinant of Q times Q transpose is equal to the determinant of the identity matrix. What is the determinant of the identity matrix equal to? 1? Yep. And then on the left-hand side, I've got the determinant of a product of two things. How can I rewrite that? Yeah, determinant of each piece, right? So I can rewrite the left-hand side as determinant of Q times the determinant of Q transpose. And what do you know about a determinant of a matrix and determinant of its transpose? What's true about that? They're equal to each other, right? So now I just have determinant of Q squared equals 1. So what should I do to both sides of the equation? Take the square root, yeah. When you take square root of both sides of the equation, you get plus or minus. Yeah, well, that's where the plus or minus one comes from. So this one was just playing around with the different properties of the determinant. It's a short little proof, but again, it gets at a couple fundamental properties of the determinant function. Remember when we defined the determinant function, we said that we wanted the determinant of the identity matrix to be 1, right? That was our scale factor. And then, of course, all the methods that we've used to find determinants, we would get 1 in that case. This talks about determinant of a product. Determinant of a product is the product of the determinants, and the determinant of the transpose is the same as the determinant of the original. So there's, even though it's a short little proof, it's got 3 different concepts in there for what we talked about for determinant functions. Kind of nice. It's a nice little problem. Other questions? Yeah, Madeline.
8D, it's determinant of negative 3a. I thought it would be negative 3 to the first time of the determinant, but in the answer it's divided by the determinant. Is it because of the negative?
I have the wrong answer in there? Check my answer key. I have no idea why I have that. No, it should be multiplied. Yeah.
Okay.
It should be it should be negative 3 to the 5th times the negative 144. Yeah. I'm wondering if at some point I had A inverse in there and I deleted it, because that would be the answer I have is the determinant of negative 3 times A inverse. So I'll get that fixed too. Thank you for pointing that out, because you are exactly right. That's yeah. Yep. What bothers me is that I use these reviews from semester to semester and nobody's pointed it out until now. So.
Must just be the best class you've had.
What's that?
Must just be the
Best class I've had? Absolutely. They only get better and better. Other questions? Yeah, Lainey.
When it asks us to find the eigenvalues, is that like, do you want us to just solve for like the lambda in that case, or do you want us to then plug it back in?
So if it just asks for the eigenvalues, you can just find the lambdas. If it asks for what the associated eigenvectors are, is when you plug it back in and solve the system. Other questions? Studying going okay? Yeah. Again, it shouldn't be too big of a surprise of what's on the exam, right? We've talked about determinants and vector spaces and subspaces. So, guess what's going to be on the exam? Okay, well, and eigenvalues and eigenvectors too are in there. But if it's an eigenvalue, eigenvector problem, it'll be short because we're going to concentrate more on eigenvalues and eigenvectors later in the semester. Got a whole chapter devoted to that later on. So right now we're just kind of doing the preliminary thing. So something with eigenvalues will be very short, like find them kind of thing, right? It's going to be something small. We're not going to do a lot with it right now. No other questions? All right, well, let's continue our discussion of vector stuff. Go on here. So remember last time we talked about spanning sets for different sets of vector spaces or for subspaces. Remember when we do the span of a set of vectors, we take the set of all linear combinations of the vectors, right? That's what a span means. You have a set of things, You try to create every single possible thing that you can by doing additions and scalar multiplications. One of the reasons why we like spanning sets is because it guarantees that we can write of any vector in your space in terms of a finite set of things. That was the whole goal of that. It was the uniqueness part. So today we're going to talk about the uniqueness part. So we did existence last time with spanning sets. Today we're going to talk about linear combinations, or excuse me, linear independence. And I just realized that I forgot to put this on the my computer screen here. So let's see if I can do that real quick. Maybe. What's that?
I said gasp R studio.
You don't like our studio?
I'm fine with R studio.
Let's see if I can find this file so I can send it to OneNote real quick. Sorry about that. I realize that usually I use the document camera in a lot of classes, and since I'm recording things, if you want to go back and look at it, it might be helpful if I actually had it on the computer. So I apologize. Should be able to do this. Perhaps. Did it do it? Well, that was weird. Did it actually do it? It went to OneNote, but I don't see where it... That was weird. Let me try this again. Oh, there it is. It was off to the side. Great. All right, cool. We got it here. Where is it? Here we go. Okay. All right. I know I have to remember it here. I've used this in previous class. One thing that 2020 did was maybe create a lot of videos and create a lot of handouts, so I might as well use them again, right? Okay. So anyway, so this first part is just the definition of what it means to be linearly independent. Okay? So what it says is that if we have a linear combination that equals the zero vector, so that's important, right? When we're talking about linear independence, we're talking about a linear combination that gives me the zero vector. If that's the case, then it's necessary that the coefficients, the constants that we're using for our linear combination are all zeros. Okay? So let's say we wanted to show, and this is say, let's do number 36. Do it there. 36 on page 184. They give you a set of vectors in R3, and that set is -4, -3, 4, 1, -2, 3, and 6, 0, 0. And the problem asks, is this set, bless you, is as linearly independent? And I'm going to abbreviate linear independent as LIN and IND. Mainly because we know that I'm lazy. All right, so if we want to see if something is linearly independent, then we need to start with looking at a linear combination that gives us the zero vector. So if I do C1 times the first vector, C2 times the second vector, and C3 times the third vector, and I want to get the zero vector out in the vector space that we're talking about, these vectors are in R3. So the 0 vector in R3 is 0, 0, 0. So we start with this linear combination that gives us the 0 vector. Now this should be giving us thoughts back to what we just did on Monday. On Monday, we were looking at linear combinations that gave us any possible vector in the space, right, to create a span. This one, we're looking at a linear combination to give us one specific vector, the 0 vector. Now, certainly, there always do exist constants that work, right? I can always use zeros, right? We're trying to figure out, is there another possibility, or is that the only possibility? And we'll see why we care about that here in a little bit. Okay. So, much like a homogeneous system, we know that there always is a solution, right? Every single homogeneous system has at least one solution, always has the 0 solution, right? Same idea here with linear independence. There's always at least one combination that gives us the 0 vector. We're just trying to see if it's the only combination. All right. Much like what we did on Monday, when we had this set up, what did we do next? We wanted to show that something was a spanning set. What did we create next? Good. We created a system of linear equations, right? What system would come out of this one? What system would you get out of this one? You should have 3 equations. See, wait, go ahead, I thought I heard you. Sorry.
A equals 1 plus 1 C2 plus 6 C2 0.
Good.
Negative 3 C1 minus 2 C2 plus 0 is equal to 0.
Okay.
4 C1 plus 3 C2 is equal to 0.
Good. Exactly right. That would be the linear system that we got out of that, right? We equate the first components, equate the second components, equate the third components, right? What kind of linear system do we have now that we see on the right hand, since we have zeros all on the right hand side, what kind of system do we have? Since they're all zeros here, this is homogeneous, right? Okay. So remember, there's always, just like I mentioned a minute ago, there's always at least one solution to any homogeneous system. We're trying to see if there's exactly one, right? How do we get infinitely many solutions for a homogeneous system? What happened? So it wasn't just a row of zeros, because it's possible I could have more rows than columns, but you're thinking about they're all along the right lines. So what will we do with this if we were trying to solve it? What will we do? Yeah, make a matrix and row reduce. What tells you in the reduced row echelon form that you have infinitely many solutions? See? Yeah, that's it. Yeah, there's a missing pivot, right? I got a free variable, right? If it's only going to have the trivial solution, we need a pivot in every single column, right? I need to make sure I don't have any free variables. Notice that's the analog for what we did for spanning sets, right? Spanning set, to make sure it spanned, we needed a pivot in every single row. For linear independence, we're going to need a pivot in every single column. Yeah. So it's the same idea here. We're going to make our matrix. I don't care about the zeros, because again, if I've got a homogeneous system, if you have a homogeneous system here, pardon me, these zeros aren't going to change when you row reduce, right? So I only need to really type in the matrix of the coefficients. So I want to do that and put that in reduced row echelon form, right? We agree with that? Okay. All right. Notice, if you do that, you can do this on your calculator or an R, but I can also do it pretty quickly just by looking at it. Ignore the first row. If I'm looking at these two vectors here, I noticed that this one's not a scalar multiple of that one, right? So if I just played with these two and ignored the top, I would get a 1, 0, 0, 1 here. Just by doing the row reduction, right? And then the last one, we get a 1 over here, because I can't kill this off with those zeros. Right? So if you put I would assume you use your calculator anyway, but this will reduce to that. You can go through the work, or you can put it in your calculator, but it's not too hard to see that I can never get rid of this 6 in this column, and these are not multiples of each other. Right? So I would get the identity matrix when we reduce. So we get a pivot in every column. Pivot in every column tells me this has only the trivial solution. If it only has a trivial solution, then the only way to get this linear combination to work is to use the zero vector, or excuse me, to use each constant being a 0. By the way, does this set also span R3? What we talked about on Monday, does it also span? Yeah, because there's a pivot in every row, right? So this set both spans and is linear independent, and that's going to give us another name after break. But notice what that means. Remember, we talked about this on Monday. If it's a spanning set, there exists a linear combination that gives us every single vector in the space, right? Linear independence is going to give us something also important. The kind of a dual notion of existence is what? Usually if we talk about things in math, we try to prove existence and uniqueness, right? Right? So what this is going to tell us is that if I have a linear independent set that spans, there's one and only one way to write each vector in terms of the set of vectors that we have. Okay, that's what kind of leads into what we're going to talk about here in a minute. All right, any questions about what we did here, how we formed this? Notice again, do you see any here with the columns again and the original vectors? Notice we made the matrix by making them into columns again, right? Same idea we did for spanning. Good news is then you can check if it's linear independent and spans at the same time. You only have to do it one time. Now the only hope you have that it's going to do both is what has to be true. What kind of matrix are you going to have if it's going to both get a pivot in every row and a pivot in every column when you row reduce? It has to be square, right? So that you can get the identity matrix. Okay. We're also leading into adding some more conditions to our big mega theorem. Okay. All right. Let's look at the next one. We're talking about 3 matrices in M22. So 3 2x2 matrices, and asks, is this set linearly independent in M22? Same idea, same exact idea. We want to look at a linear combination of these matrices that gives us the 0 vector. What is the 0 vector in M sub 22? Good, exactly right. It's the 2x2 matrix of zeros. Fantastic, exactly. It's important to know what your 0 vector looks like if you're going to set it equal to the 0 vector. Now, it should be, in these problems that we're doing, it should be what you would expect it to be, right? We're not doing weird spaces here, okay? But still, it's important to know what it looks like if you're going to try to set up this system of equations. All right. How many equations are you going to get in this case?
4.
We're going to get 4 of them, right? You're going to get an equation for every single entry, aren't we? Tell me one of them.
C1 minus 3C2 plus 5C3.
Oh, I don't want to write that last C equals 0, right? That's one of them. And then do the same thing for the other entries, right? That was upper left. If we do upper right, we get negative 3C1 plus C2 minus 3C3 equals 0. Do lower left, 4C1 plus 6C2 minus 7C3 equals 0. Last one, C1 minus C2 plus 2C3 equals 0. That would be the system of equations we set up, correct? Now, the good news is that this is kind of an intermediate step that I'm assuming you're going to skip eventually. Okay? Because what are we going to do with this particular system now? Make a matrix, right? We got 1, -3, 5, -3, 1, -3, 4, 6, -7, 1, -1, 2. Right? Those are the coefficients. Do you notice, again, anything about the columns of this matrix and the vectors that you're dealing with? Yeah, each column is just the entries in the matrix, right? By the way, I've written these as 2 by 2 matrices, but is there any real difference in terms of the vector space? Is there really any difference between writing these as 4-dimensional vectors or 2 by 2 matrices? Any difference at all? No. So from an algebraic standpoint, as vector spaces, the 2 by 2 matrices have the exact same structure as R4 does. In algebra, we call that being isomorphic. What's the Greek in there, right? Iso, same, morphic structure. Okay? We deal with isomorphic things in algebra a lot. Basically, they are the exact same thing, even though they look different. I mentioned the other day, they are the same picture, right? What isomorphic means algebraically, or mathematically speaking. Before I do anything, you should be able to tell me immediately one of the 2 things that we're learning about can't happen. Is it impossible for this to be linearly independent, or is it impossible for it to span before you do anything? So it's one or the other, right? So it's impossible for it to do one of them. What do you need to see when you row reduce for a span? Pivot every row, right? For linear independent, we're looking for pivot in every column. One of those 2 things is impossible before I even do anything. Which is it? Pivot every row, right? Remember, pivots go down and to the right. I run out of room, right? I cannot get a pivot in every row, so this cannot span, period. Okay? This is another concept we're going to talk about after break. So before you even do any work, you don't even have to look at it. You know that it's not going to span. But we need to row reduce it in order to check whether or not it is linearly independent. I do want to show, I would do this in R because it's quick with the column bind command, but I want to show this on the calculator specifically because this shows a little bit of a quirk in your calculator. And this is the reason why I wanted to do this particular example. Get the little calculator loaded up here. Where is my calculator? Why is my oh, maybe it's in this folder, I think. There. Where is my calculator? There it is. Don't know where it was. What? No, I don't. Just go. Just go. Oh, what is this thing doing? Why is my calculator not working? Worked the other day. Oops, not there. Should have looked to see where it was. I don't know why I don't have my. I put a link on the desktop. Yeah, I did. Here it is. Guess I should have looked there first. Sorry about that. All right. Let me. All right. So if I hit the wrong thing. If I put this matrix in as a 4x3, something strange is going to happen here in a second. All right. So we've got 1, -3, 5, -3, 1, -3, 4, 6, not 9, although it would still illustrate what I want to illustrate. -7, 1, -1, 2. All right. Again, we want to try to put this in reduced row echelon form. So oh, yeah, I know. I didn't mean to hit enter twice. Calm down. All right. I get an invalid dimension. Okay. Whatever algorithm they use in the TI calculators to put things in reduced row echelon form will not let you row reduce a matrix that has more rows than columns. Okay. So there's a workaround that you have to do to be able to do it, and it's just basically fill in as many columns as you need with zeros. Okay. All right. So the easy way to do that is just to go back into your matrix thing, go over to edit, just change this to a square matrix and make it 4x4. And it should just add a column of zeros in there, and then it'll row reduce it just fine. Just know that you need to ignore that last column. It's a quirk of the calculator, which is why I wanted to show it. And then I was going to get really irritated if I couldn't get it to work. It's a quirk of the calculator. If you have more rows than columns, it won't reduce it. So the workaround is to fill up the columns that you need to make it square with zeros and ignore them. Okay. So in particular, for this one, I don't want to try to do any interpretation with those zeros being there. So ignore those and just look at the first 3 columns because we have 3 matrices to start with. Did we get 3 vectors to start with, which were matrices. Do we get a pivot in every column? No. All right. So if I go back over to this, we know that was a half and -3 halves. So there's our reduced row echelon form for that matrix. It is not the row of zeros that's the important thing here. Now, the row of zeros is important for span, but not for linear independence. Okay? The important thing is that we've got this last column has a free variable. It represents a free variable. We don't have a pivot there, right? So this is telling that the set is not linearly independent. Or another way to say that is linearly dependent. Questions on that at all? Okay. The reason why we call it linearly dependent is because looking at this, and we've had problems like this before, looking at this, I can tell how to write the third matrix as a linear combination of the first 2. Okay? So if you were to if you labeled your original matrices up here, say A, B, and C, just to give them names, then this tells me that C is equal to 1/2 of A minus 3/2 of B. Just reading these coefficients off here. So I can write one of the vectors as a linear combination of the other 2, which means that this vector C depends on A and B. So that's where the linear dependence comes from. So the reason why we say linearly independent means that I cannot write any of the vectors in terms of the other ones that we have in the set. That's what the independent, so it's independent of the other ones. That's where the name comes from. Is okay? All right. So talked about how to figure out if whether or not things are linear independence. Why do we care? I've already alluded to this, right? Say we've got a set of vectors v1 out to vn, and I have two linear combinations that give me a vector w. I've got two ways here that we've written w as a linear combination of the v's. How would I get a linear combination of the v's that equals the zero vector? Subtract them, right? Just subtract the two, I'll get 0 on the right-hand side, correct? So if we subtract these two equations, we get C1 minus D1 times V1, C2 minus D2 times V2, Cn minus Dn times Vn equals the zero vector. I now have a linear combination of the v's that gives me the zero vector. If your v's, if the set of the v's is linearly independent, what can I say about each of the constants? What do they have to be if it's linearly independent? They all have to be 0, right? So if your v1, v2 out to vn is linearly independent, then C1 minus D1 has to be 0, C2 minus D2 has to be 0, all the way to Cn minus Dn has to be 0. Or C1 equals D1, C2 equals D2, Cn equals Dn. Whoops, I hit the scroll bar. So if they're linearly independent, did I have two different linear combinations that gave me W? Or did I just write the same linear combination twice? I wrote the same one twice, right? So what does that say about the number of ways that I can write W as a linear combination? How many ways is there? 1, right? So this is why we care about linear independence. The linear combination that gives me any vector is the only way to do it. It's unique, right? So in this case, if we have linear independence, the linear combination of the v's that gives W is unique. So this is the uniqueness portion of what we want. Spanning gives us existence. Linear independence gives us uniqueness. So if we have a set that does both, we get both. We get linear, we get unique and exist, right? So everything, when we have a set that does both, we get a way to express everything in the vector space uniquely in terms of the set of vectors. Yeah. So that's going to be a concept we'll talk about after break. Is that okay? So this is why we care about linear independence and why we care about span. Let me just talk about the first part of this theorem here. For the first part, it says here that any set that contains the zero vector is necessarily linearly dependent. So if you have a set of vectors that contains the zero vector, say that's my set. Can you give me a linear combination using vectors from that set where not all of the constants are zero, but I get the zero vector out? Can I form a linear combination of all the vectors using vectors from that set where not all of the constants are zero and get the zero vector? What would I use? Yeah, just use a multiplication. I can use anything that I want for a zero, times zero, can't I? So notice that we would have, say, 0v1, 0v2, out to 0vn plus, I don't care, 7 times 0. What do I get? 0, yeah. There's a linear it doesn't matter what the constant is. I just randomly picked 7. Okay. It doesn't matter what this constant is, correct? So I found a linear combination that gives me the zero vector where not all of the constants are zeros, right? So that means it's not linearly independent, so that's why it's linearly dependent. Okay. So since this is not zero, that constant right there, that tells me my set is linearly dependent. So in particular, we never want the zero vector in a set of things that we're trying to generate. It doesn't do us any good, right? I can't generate anything from the zero vector except the zero vector. So there's not really any point to put it in there. I can always generate the zero vector by using zero constants. I don't want to use it to try to generate new things because it's not going to generate squat. This okay? All right. We'll do more of this after break, but I wanted to give a nice little introduction into this because it's going to lead into the next topic that we'll talk about right after break for vector spaces. All right, so no class Friday, of course. Exam, determinants, eigenvalues, eigenvectors, briefly, just a little bit of it. Vector spaces and subspaces. Okay? All right. Have a good break, everybody. If I forget to tell you when you come in and take your test.